So atoms combine to form compounds. We represent compounds with chemical formulas. Chemical formula tells us what elements are present in that compound and the relative quantities of atoms or ions that each is present in. So we use subscripts and the element symbols to make chemical formulas. So the formula for water is H2O. So we've got H for hydrogen, O for oxygen. We've got the subscript 2 after the hydrogen, meaning there are 2 hydrogen atoms. And there's nothing after the oxygen, meaning there's 1 oxygen atom. We often leave out the number 1 because we don't really need to write it, so why bother? Here's another one, carbon tetrachloride, CCl4. So C is for carbon. There's 1 carbon. If there were no carbons, we wouldn't write the element symbol. And if there was more than 1, we'd write some other number. So just the element symbol tells me there's 1 carbon atom, and then Cl4, there are 4 chlorine atoms. Questions? We have different types of chemical formulas. There are empirical formulas, molecular formulas, and structural formulas. And you could equate these to different ways of identifying people, right? You can go by a nickname, your first and last name, your full name. You could use your social security number, your date of birth, your student ID number. There are different ways to identify an individual person. So we have different ways of indicating a specific compound. The empirical formula, the word empirical means from experiment. So the empirical formula gives us just the relative number of atoms of each element. It gives us a ratio. So an example here is hydrogen peroxide. Each hydrogen peroxide molecule has 2 oxygen atoms and 2 oxygen atoms. Okay, start over. 2 oxygens, 2 hydrogens. Okay, so it might look something like that. An empirical formula gives us a relative number, the lowest ratio. There are actually 2 oxygens and 2 hydrogens, but that's not the lowest ratio. The lowest ratio would be 1 to 1, so 1 hydrogen to 1 oxygen. That's the empirical formula. It's like a reduced fraction, the lowest ratio.
How do you distinguish that from a hydroxide when you're trying to look at it?
That's an excellent question. How do we distinguish this from the ion hydroxide, right? So hydroxide is OH minus. So this minus means that hydrogen and oxygen together have 1 extra electron. And that's going to make them different from a hydrogen-oxygen without a charge. And there actually is no stable molecule of 1 hydrogen and 1 oxygen. So that just doesn't even exist. But OH minus and HO, if you're not thinking about it real carefully, what is different about those? Well, details are very, very important sometimes. And here's an example. That negative sign is really important. There are other formulas, like there's a compound, NO2. That's a compound, and there's also an ion that's NO2 minus. They have different names. They have different properties. They are different things. And it's all because this one has 1 extra electron. Does that answer your question? Oops. So that's the empirical formula. A molecular formula tells us the actual number of atoms of each element. So for hydrogen peroxide, the molecular formula is H2O2. In 1 molecule, there are 2 hydrogen atoms, 2 oxygen atoms. From the molecular formula, we can identify what the empirical formula is. For C4H8, We can look at the ratio of 4 to 8, and those have a common factor of 4. We can divide each of them by 4, and so we can say the empirical formula is CH2. Turns out there are a lot of compounds whose empirical formula is CH2. They've got different molecular formulas. B2H6 is a molecular formula. Here we can reduce 2 to 6 to 1 to 3. So this is the empirical formula for that one. For carbon tetrachloride, 1 to 4 is already in the lowest whole number ratio, and so the empirical formula and the molecular formula are exactly the same. We're going to learn towards the end of this chapter how you can figure out from the empirical formula what the actual molecular formula is. And you need one more piece of information. You can't tell just from looking at the empirical formula. A structural formula gives us a little more information. It is like the molecular formula. It's going to show us how many atoms of each element are in a molecule, but it's also going to show us how are those connected. Are they in a long straight line? Are they holding hands in a circle? What are they doing in that molecule? We use a single line to represent a single bond, a double line for a double bond, and a triple line for a triple bond. So there are a lot of confusing things in chemistry. We're not trying to be confusing on purpose. Single line, that's a single bond. Yes?
For the empirical, how do we work for a odd number?
Like if you had 3?
Yeah.
Okay, so that could happen. Let's make up an example. What if we had C6H6O2?
Well, like the numbers like it'll be like C5H3.
Okay, if it's like C5H3, then this is the lowest ratio, 5 to 3. There's no common factor other than 1. And so then the empirical formula and the molecular formula are the same. Here, when we've got more than 2 elements, if the ratio 6 to 6 to 2, if all of those are divisible by the same factor, we could reduce that, and that would be C3H3O, would be the empirical formula.
Can you only reduce it using empirical formula?
Yeah, you would only reduce it if you're looking for the empirical formula. So we have these different types of formulas, and the one that we use in any given situation depends on how much information we want to communicate. So it's like your name. Somebody asks you your name, and you might just give them your nickname, because all they need to know is, what should I yell to get your attention? But other places, you're going to give your first, your middle, and your last name, because it's a legal situation, and they need to know exactly who you are, right? So we use chemical formulas, the different types, like we would use different forms of our name. Communicates different amounts of information. So this is the sort of thing we should be able to do for an exam. Write the empirical formula for the compounds represented by the molecular formula as shown. Okay, so C5H12. Can that ratio be reduced? No. So here, the empirical formula is C5H12, which is the same as the molecular formula. How about Hg2Cl2? That would be just HgCl. How about C2H4O2? CH2O. Okay? When I look at these two formulas, I can be pretty sure that those are molecular formulas because they're not in the lowest ratio. If I look at one that's in a lowest ratio, I can be certain that it is an empirical formula, but it may or may not be the molecular. We also represent compounds using models, and this gives us more information, but it's more tedious to put down because you either need a picture of a model, take a picture of something you built, or you need to draw a picture, and that takes longer than just writing a formula. So two main types of models. One is a ball and stick model. So the atoms are represented with balls and the chemical bonds are represented with sticks. These are like chemists' tinker toys, right? And the atoms, the balls, and the sticks will be arranged in a shape that reflects the shape of the molecule. To make things a little less confusing so we don't have to label everything all the time, we typically use these colors to represent these main elements. You do not need to memorize these colors, but these are the colors that are used in the book and in the model kits that we have around the department. Carbon's always represented as a black circle, just because we decided to do that. We can also have space-filling models. So here is an example of a ball and stick model for methane. This is the molecular formula, CH4. Here's the structural formula telling us that there's a carbon in the center and all 4 hydrogens are bonded directly to the carbon. Not understanding the characteristics of these elements, there are lots of other ways that you could put these two elements together. You could say, well, what if they're like this? Or what if, we've got something like this, and they're like holding hands or something. All kinds of weird things you could draw, right? Those are completely bogus. This is what it does. The ball and stick model shows us that this is not a flat two-dimensional molecule. This looks flat, doesn't it? It's in the plane of the screen, it's just flat. The actual molecule is three-dimensional, and we'll learn later this shape is called a tetrahedron. The space-filling model gives us an even more accurate representation of what the molecule would actually look like. So here, instead of discrete balls, we have these balls that are seeming to overlap each other. They're filling up the space. So in an actual molecule, there's not this little bond sticking between these two. They're actually, because of that bond, they're sort of merging into each other. And here's a table from your textbook showing ways of representing 4 different compounds. So let's just look at glucose. This is also known as blood sugar. The empirical formula, the molecular formula. There are actually a lot of different compounds that have that same molecular formula. The structural formula tells us how those individual atoms are put together. The ball and stick model helps us to understand the shape, as does the space-filling model. The space-filling model has a disadvantage in that it is, the space is filled in, and so you can't necessarily see what's on the other side. That's what's nice about a ball and stick model, is you can see that hydrogen that's over in the back. Here, there's some hydrogens hiding on the back that you can't see just looking at it on a picture of it. This molecule has some double bonds, so those are represented with a double line. This is a triple bond. Any questions?